This video will design the tension member. Okay, there may be two types of question. One is design the tension member and another is calculate the design tensile strength. So I am doing the first calculation of the design tensile strength. In the other type, what it is given and how to do it, I will just give a short intro in the end of the video. So the very first step is to open the Codal book, and in page number 32 the process is given simply and briefly. uh, you have to go line to line, okay, but you have to introduce two more equations to find two more values for better efficiency of the designing. Okay, I will list down the value from the given property class, that is f. Now with this data I will start with design shear strength. Okay, design shear strength, which we know from the bolted connection also. Design shear strength VDSB is equal to FUB under root 3 gamma MB ANS NS plus ANB NB. Okay, so FUB is equal to 400 under root 3 1.25, this gamma MB for bolt. ANS, this is a case where number of shear plane intercepting the thread is equal to 1. There is no intersection of the shank with the shear plane, so NS will be 0. Number of shear plane intercepting shank will be 0, so will be the total value here, and we'll consider this only, and we'll multiply it by 0.78 by the diameter of the threaded portion, d square by, so diameter is 16 square by 4. Okay, why 0.78? Because the threaded portion will have some hollow spaces, so that is reduced, so it will be 0.78 pi d square by 4 multiply by 1, that is number of shear plane is equal to 1. We can calculate 0.78 multiply by pi 16 square by 4 multiply by 400 under root 3 28.974 kilonewton. This is for the single bolt. Total shear strength is equal to number of bolts multiplied by VDSB, that is 28.974. so this is the value in Newton, okay, but I am doing in terms of kilonewton, so divided by 1000. Now the second is bearing capacity. This question, pitch is not given, you have to calculate it. Okay, for calculation of pitch and E, there is equation P should be greater or equal to 2.5 times of diameter. So 2.5 multiply by 2.5 times multiply by D 16 40. Okay, it is 40, and I'm taking as 50 mm, and E should be greater than 1.5 ED naught, so which will come as 27 mm, provide it as 30 mm. Okay, so this is the pitch and end. Then we can calculate the value of KB, which will be minimum of this. So on substituting this value, I will get this as 0.55, 0.675, 1 and 0.975. minimum of this is 0.55, so kb is equal to 0.55. Substitute the value of kb in this dpb, 2.5 times kb 0.5, d is the diameter which is 16, t is the thickness of the section which is given as 6, okay, multiply by minimum of fu or fub. In this case fub is minimum, so 400 by 1.25. okay, now this value comes as 42.2 kilonewton, and we know minimum of these two will be the bolt value. So before that, total bearing capacity that is vdpb total is equal to 42.2 num by multiplication of number of bolts, so it will be equal to 253.4 kilonewton. okay, now we will follow the codal provision. We will calculate yielding strength due to the yielding. okay, so third is design strength due to yielding of cross section. And in the codal provision, if you see, you will find at page number 32, which says TDG is equal to AG Fy gamma m naught. So for gross area is on an unequal leg, 100 into 75. So you have to go through this. In case of unequal leg angle, 100 into 75 into 8, gross sectional area is 100 into 75 into 6, gross sectional area is 10.1. okay, you can see here 10.1 centimeter square. So 10.1 centimeter square, so converting into mm, Fy 250 divided by gamma m naught 1.1, so this comes as 229.94 kilonewton. The second step is design strength due to rupture of critical section. We are designing for a single angle, so you have to come here. okay, this is for plates and this is for threaded rods. Now we are doing for the single angle, so come to this value. okay, so there are various new terms to us. The very first is beta, which is given by a formula 1 minus 1.4 minus 0.076 W by T Fy by Fu Bs by Lc less than Fu gamma m naught Fy gamma m1. okay, and this value should be greater than 0.7 but less than this. okay, so what are these terms? Wt, Bs, Lc. okay, I will make clear. So if this is the leg angle, okay, and connected to a gusset plate, the angle or the leg of the angle connected to the gusset plate is known as connected leg, and the leg which is not connected is the outstanding leg. And you will have the dimension. So the dimension of the outstanding leg is termed as W. okay, width of the outstanding leg. T is the thickness of the section. Bs, if we see here, Bs is the shear leg width. okay, so if this is the leg angle, okay, it will have a axis like this, but the stress distribution does not pass through the center of gravity, hence shear lag occurs between connected leg and outstanding leg. okay, this is the concept general you have to understand here. So Bs is equal to shear lag width, which is given by W, and here we have a bolt. If this is W1 plus W1 minus thickness 2T. okay, t by 2. Okay, why t by 2? One of the thickness lies in the outstanding leg and one thickness of the connected leg is reduced. Okay, this part won't face shear lag. Okay, so bs is equal to w plus w1 minus t2 by 2t by 2. So finally we'll get w plus w1 minus t. In welded connection, bs is equal to w, and w is the width of the outstanding leg. Okay, that is the difference. And if you are provided with the other section such as double angle, you may be provided with a double angle in this case also. Okay, double angle, then gusset is also governed by shear lag effects. Another term, LC, this is the distance, or we can say length of connection. Okay, length of connection. So if this is the connection, okay, the projection, okay, this one be, if this is the projection, length of connection will be from center of the first bolt to center of the last bolt. Okay, now substitute the value here. Beta is equal to 1.4 minus 0.076. W is, in our case this is 75. Now what is W1? This is the gauge distance. Okay, G, gauge distance, and this is taken as the value smaller. Okay, for example, if it is 100, I will provide this 40 and the upper value as 60 for the safety purpose. So 0.076, I will provide this W as 75, thickness 6, Fy 250 by 410, BS. Now provide W as 75, W as 40 minus thickness 6, so 109 mm. 109 divided by LC, length of connection 1 2 3 4 5. From this to this, one bolt will reduce, one bolt size, so length of connection will be number of pitch 1 2 3 4 5. So number of connection 5 multiplied by pitch distance, which is 50, so it will be 250 mm. 250 should be less than FU 410 1.1, 250 into 1.25 should be greater than 0.7, and this value comes as 1.14, which is, and this value comes as 1.44, greater than 0.7. so this value satisfies both condition. Okay, now coming to this, we have to calculate ANC and AG naught here. So what is ANC then? Net area of connected leg, gross area of outstanding leg. So I will start with the outstanding leg. Gross area, so we don't have to reduce any hole size or any bolt size. So it is, width is 75 multiplied by the thickness, is it? But okay, 75 multiplied by the thickness, which is 6. But in the case of this figure, I made you clear about the fact that this length is not a part of outstanding leg, so you have to reduce this length or this area, which is T by, or this is thickness, so thickness 6 by 2 into 6. So as a whole, if we see 75 minus 6 by 2 into 6, okay, so it is equal to 432 mm square. In case of net area of connected leg, you have to reduce the whole bolt size. Okay, this bolt size or hole size we have to reduce. 100 minus nominal diameter 16, so it will be 18, minus this area has to be reduced, so 6 by 2 into 6, it will be equal to 474, mm square. Now we have all this value, ANC, FU, okay, AG naught, FY, gamma m naught, beta. Then we can calculate the value of TDN. I'll just write it directly. If you want to make sure, just put the value and you will get 251.85 kilonewton. Okay, this is the value of design strength due to rupture of. Now the another is design strength due to block shear. What is block shear? It is a combination of tensile and shear failure. So step number 5, design strength due to block shear. You will get two equations there, and minimum of these two value you have to take. If we see in this equation, you will find AVG, ATN, AVN and ATG. So what are these? AVG, AVN, ATG, ATN. So these are the shear area, and one is about the gross and another is about net. Similarly, this is tension area. One is gross, another is net. So if this is a plate provided with bolt in this way, the shear failure occurs in this direction, parallel to the applied force, tension. Okay, this is the shear failure, and for tension failure it is perpendicular to the direction of tension. We have to understand these two terms while calculating the area. Now gross area in the direction of, so what we have to say is this is the block shear. Okay, this term has to be understood. And block shear with respect to the gross area. Now gross area of this shear, this is the shear failure, as I have already said. So you have to multiply the pitch distance, okay, and end distance. So this is the pitch, this is the end distance, and this is the pitch distance. So in our case, we have been provided with 6 number of bolts, this downward being the outstanding leg, and it will have a thickness downward, so it doesn't fail in the downward direction, rather it fails in the upper direction. This is the shear failure. Now for tensile failure, it has to go perpendicular to the direction of load applied. Okay, so if you see in our figure, this is this projection of this, so it is this line is here, and this line will be acting in this way. So the failure does not occur in the downward direction, rather it fails in the upward direction, and this will be our block shear. Okay, so this is our block shear. Then AVG will consider this end distance, which is 30, plus we are neglecting this distance and considering this up to the central point. Okay, so 1 2 3 4 5 pitch distance, okay, plus multiply by the thickness, that is 6, so we get as 1680 mm square. AV and net area. Now the diameter of the holes has to be reduced from the total length minus, as I have said, till the middle, okay, center of the last bolt. So number of bolt is 6, but half bolt is taken for the last case, so 5.5 multiply by nominal diameter is 18 into 6, okay, as a whole. If we see, it comes as 1086 mm square. ATN, tension area is this, and for tension area gross, ATG, the gauge distance, if we see, the gauge distance here is 40 and the remaining distance is 60, so we have to multiply 60 by the thickness, 6, so it's 360. And for net area, the half hole has to be reduced. Okay, so 60 minus 0.518 into 6, 306 mm square. Then we have the formula for TDV, AVG. I guess you know all the value now. Okay, so I will write directly. For the TDV upper one, I am writing TDV1. So the value comes as 310.72 kilonewton, and for the downward value, it comes as 266.99 kilonewton. So from this two value, the minimum value is taken as the design strength. So TDV is equal to 266.99 kilonewton. Hence, the minimum of all the value, okay, the minimum of the all steps we have: design shear strength, this is the total shear strength first, total bearing capacity second, and this is the third, fourth, this is the fifth. So minimum of all this value is taken as the design strength of the tension member, and we see the minimum is 173. So design strength is equal to 173.846 kilonewton.